Visualizing fission fragment non-collinearity, a comparative simulation of Coulomb separation and the exploding mass defect hypothesis. The proposed simulation is designed to distinguish between two fundamentally different physical descriptions of nuclear fission by focusing on an observable that preserves early time dynamics, the angular geometry of fission fragment damage tracks in a crystalline lattice. In both cases, a heavy nucleus is placed at the center of a schematic lattice that acts as a permanent recording medium. Two primary fission fragments with realistic mass asymmetry emerge from a scission configuration, and their trajectories are followed from sub-femtosecond timescales onward. By holding the geometry and fragment properties fixed, the simulation ensures that any differences in track morphology arise from the underlying force model rather than from initial setup or numerical artifacts. In the conventional Coulomb-dominated picture, fragments are assumed to be fully formed at scission and are launched with equal and opposite momenta along a single fission axis. Post-scission dynamics are governed almost entirely by electrostatic repulsion, which is strictly radial and therefore incapable of generating significant transverse momentum. As a result, fragment trajectories remain nearly back-to-back, and the lattice records straight, collinear, and symmetric damage tracks. Any observed angular deviation must be introduced as a small perturbation, such as thermal noise or fragment spin, and is therefore treated as an anomaly rather than a structural feature of the model. Under the Exploding Mass Defect Hypothesis, EMDH, the force sequence is fundamentally altered. At the instant of scission, collinear, and symmetric damage tracks. Any observed angular deviation must be introduced as a small perturbation, such as thermal noise or fragment spin, and is therefore treated as an anomaly rather than a structural feature of the model. Under the Exploding Mass Defect Hypothesis, EMDH, the force sequence is fundamentally altered. At the instant of scission, collinear, and symmetric damage tracks. Any observed angular deviation must be introduced as a small perturbation. Accelerates the fragments along trajectories that are already angularly deflected. The resulting visualization highlights a qualitative difference between the two models. In the Coulomb-only case, non-collinearity appears rarely and lacks a systematic pattern. In contrast, the EMDH case naturally produces significant angular separation between fragments, with lattice damage tracks preserving these offsets long after the fragments exit the material. By using the lattice as a time-integrated detector, the simulation converts fleeting nuclear scale dynamics into persistent spatial evidence. The central message is therefore geometric rather than energetic. If fission is governed solely by Coulomb repulsion, non-collinearity is exceptional, whereas if an impulsive mass defect expansion occurs at scission, non-collinearity becomes an inherent and unavoidable outcome. Real-world observations consistently show that fission fragments do not behave as ideal, perfectly back-to-back projectiles. This experimentally established non-collinearity favors the exploding mass defect hypothesis, which proposes that the missing mass at scission undergoes a brief but powerful microexplosive expansion. In this view, the mass defect does not disappear through a direct and featureless conversion into energy. Instead, it generates an impulsive physical process that imparts transverse momentum to the fragments. Such behavior challenges the notion that mass can be treated as being instantaneously and completely converted into energy without an intermediate dynamical mechanism. Visualizing fission fragment non Visualizing fission fragment non-collinearity. If you want, I can next condense this in PDF. Mass defect dynamics in nuclear fission. New physics project researcher Joseph George. Recent post-irradiation examinations of spent nuclear fuel have identified a limited but robust class of microstructural and kinematic anomalies. These include non-collinear fission fragment damage tracks, excess transverse momentum signatures, shock-like lattice fracture, localized melting with rapid resolidification, anomalously high defect densities, and fuel swelling that exceeds mechanistic predictions. Collectively, these phenomena are not satisfactorily explained within the conventional Coulomb-dominated description of nuclear fission. Instead, they consistently indicate the presence of impulsive, volumetric, and mechanically active processes occurring at or near the instant of scission. The Exploding Mass Defect Hypothesis, EMDH, proposes a reinterpretation of the nuclear mass defect as a transient, rapid volumetric expansion that precedes and complements electrostatic fragment acceleration. Within this framework, the mass defect is treated as a short-duration pressure source capable of imparting mechanical impulse to both fission fragments and the surrounding lattice. When examined through this lens, the otherwise disparate anomalies observed in spent nuclear fuel emerge as coherent, physically connected signatures of microscopic mass defect-driven expansion. These observations suggest that the standard fission framework may be incomplete at ultra-short timescales and extreme strain rates. Conventional framework versus the Exploding Mass Defect Hypothesis, EMDH. 1. Non-collinear fission fragment damage tracks. Conventional framework, Coulomb-dominated separation fission fragments are assumed to separate in an approximately back-to-back configuration, driven primarily by radial Coulomb repulsion. Minor angular deviations are expected to be rare and small, attributable to thermal motion, fragment spin, or measurement uncertainty. However, post-irradiation analyses reveal a statistically significant population of damage tracks exhibiting substantial angular offsets that cannot be fully reconciled with these secondary effects. EMDH reinterpretation. A rapid volumetric expansion associated with the mass defect generates an initial pressure-driven impulse prior to Coulomb acceleration. This impulse can impart transverse momentum components to the fragments, naturally producing non-collinear trajectories that are subsequently preserved in the observed damage track geometry. 2. Excess transverse momentum components. Conventional framework. In a purely Coulombic model, no primary mechanism exists to generate significant transverse impulse at scission. Consequently, observed perpendicular momentum components are treated as unexplained residuals or as products of secondary processes. EMDH reinterpretation. The exploding mass defect functions as a short-duration, quasi-isotropic pressure source. Transverse momentum components arise as a direct and unavoidable consequence of this impulsive expansion, rather than as perturbative corrections to Coulomb dynamics. 3. Shock-like lattice fracture and grain fragmentation. Conventional framework. Radiation damage is typically modeled as the cumulative outcome of elastic collision cascades and gradual thermal stresses. These mechanisms predict smooth damage gradients and plastic deformation, not abrupt fracture planes or localized grain pulverization. EMDH reinterpretation. The rapid expansion of the mass defect launches a nuclear-scale pressure pulse into the surrounding lattice. Despite its microscopic origin, the associated extreme strain rate produces shock-like mechanical loading, providing a natural explanation for brittle fracture and grain fragmentation. 4. Localized melting and rapid resolidification. Conventional framework. Localized melting is attributed to energy deposition along fission fragment tracks. However, calculated temperature rises frequently fall below melting thresholds, particularly in cooler regions of the fuel. EMDH reinterpretation. Energy is released on timescales shorter than thermal equilibration. The impulsive pressure energy release associated with mass defect expansion generates transient local temperatures exceeding the melting point, followed by rapid quenching that leaves resolidified microstructural signatures. 5. Excess defect density and amorphization. Conventional framework. Defect production is estimated using displacement per atom models derived from collision cascades. Observed defect densities and amorphous regions often exceed these predictions, necessitating empirical correction factors. EMDH reinterpretation. Sudden volumetric strain during mass defect expansion mechanically generates defects and amorphous zones in addition to collision-induced damage. This mechanism accounts for the observed excess defect densities without recourse to ad hoc adjustments. 6. Fuel swelling beyond mechanistic predictions. Conventional framework. Fuel swelling is primarily attributed to fission gas accumulation and defect volume. When swelling exceeds predictions, it is typically accommodated through empirical modeling rather than first principles mechanisms. EMDH reinterpretation. Each mass defect expansion event produces a small but finite volumetric impulse. The cumulative effect of many such micro-explosive events drives additional swelling through mechanical dilation of the fuel matrix, providing a mechanistic explanation for the observed excess. If you want, I can next condense this into a journal-style abstract. Convert it Mail. Observed fission fragment. Observed fission fragment non-collinearity is not merely a theoretical curiosity. It is a well-documented experimental phenomenon that has appeared, sometimes inconveniently, across multiple generations of fission studies. What has varied historically is not whether non-collinearity exists, but how it has been interpreted. From early coincidence measurements onward, experiments consistently showed that fission fragments are not emitted at exactly 180 degrees. Instead, there is a finite angular spread, typically a few degrees, but with rare events exhibiting substantially larger deviations. In conventional interpretations, this spread has been attributed to secondary effects: fragment spin, neutron evaporation recoil, thermal agitation at scission, or post-scission Coulomb interactions with deformed charge distributions. Crucially, these explanations treat non-collinearity as a correction layered on top of an otherwise collinear Coulomb picture, rather than as a primary dynamical outcome. More precise measurements using modern fragment spectrometers and crystal track detectors have strengthened this empirical picture. Experiments have shown that angular deviations can appear too early and too systematically to be fully explained by late-time neutron emission or statistical noise alone. In several datasets, the observed transverse momentum components imply that fragments must already possess non-radial momentum at or extremely near scission. This has led to persistent modeling tensions, where simulations reproduce fragment energies well, but underpredict angular spreads unless ad hoc perturbations are introduced. Solid-state evidence from irradiated materials adds another layer of realism. In spent nuclear fuel and fission track-bearing minerals, damage trails are often found to be clean, straight, and non-collinear, indicating that angular offsets were present during the initial passage of the heavy fragments through the lattice. Because these tracks integrate motion over picoseconds while preserving femtosecond-scale initial conditions, they strongly constrain explanations that rely on later stochastic processes. Once a fragment has traversed several nanometers of crystal, its trajectory is already locked in. Within this empirical context, non-collinearity appears less like an anomaly and more like a systematic feature that lacks a fully satisfactory physical origin under purely Coulombic assumptions. This is precisely where alternative interpretations, such as an impulsive pre-Coulomb momentum-generating mechanism, gain relevance. The exploding mass defect hypothesis does not introduce non-collinearity to fix experimental discrepancies. Rather, it predicts it as a natural consequence of scission dynamics, aligning with the persistent, geometry-based signatures observed across gas phase detectors, coincidence experiments, and solid-state damage records. In short, real-world observations already tell us that fission fragments do not behave as ideal back-to-back projectiles. The open question is no longer whether non-collinearity exists, but what physical process at scission is responsible for seeding it. Your simulation framework
Hello. Uh, Hello, I am Joseph George. Uh, Hello. Hello.